Okay, let's get right back into it. So now we're going to be going into forms of energy. Now there's a lot of different forms of energy. There is thermal, mechanical, kinetic, potential, electric, magnetic, chemical, and nuclear. Now in our class, we're mostly been focusing pretty much on thermal, mechanical, and a little bit on electric. Kinetic and potential, more or less, we'll say are zero most times. Magnetic, chemical, and nuclear, well, we're not going to deal with those at all. Now, while we deal with these in their individual components, what we care about most times in an equation is looking at how the total energy E of a system changes. We deal with how that energy changes from one form to another. We deal with how that energy is produced by burning fuels. All of those things are important to us. Now there's two different ways I can look at this. I can look at it as a macroscopic form of energy. I can also look at microscopic forms of energy. Now, macroscopic is pretty easy to think about. It's like kinetic and potential. Things move. I lift them up in the air. Even temperature is macroscopic. But microscopic is kind of where it gets a little bit confusing. Now, I'll go ahead and show how that works. So for microscopic, I'm thinking like maybe something like a nitrogen molecule. And that can do various things. It can vibrate, where these guys move back and forth. It can rotate. And it can also translate. So it has all these different forms of motion. And those forms of motion are actually connected to its temperature. Like this, the overall average motion of the microscopic particles is how we get to the macroscopic property we measure, which is temperature. So the faster they vibrate, bounce around, rotate, and translate, the higher the temperature you will feel. Now, I don't walk around with a microscope so I can be looking at how fast these things are rotating or vibrating or translating. So what we do instead is we deal with something called internal energy, which is a capital U. And that's just going to be a catch-all for all forms of microscopic energy. So every single thing you can think of, all of them, that's going to catch it for us. Now you're like, okay, well, how do we get U? Well, you can look at tables for it. They're in the back of your textbook. You can also get it as a function of temperature, which we'll learn about later on. So all these forms of energy are important to us. Now, most of you are familiar with this thingamajig here. You've plugged something in before, whether it be your refrigerator, your computer, whatever it is. And you get electricity, you can power it. But where did that power come from? Well, it might amaze you, but there are actually almost 6 different forms of energy, depending on what's producing the power, going from, in this case, a nuclear power plant all the way over to your electrical socket. So there is nuclear, which starts in the nuclear reactor itself, and that nuclear energy is from things breaking apart, fissioning. Those send off neutrons, which are kinetic. That causes the water to heat up as its temperature rises. That's thermal. It turns into a gas. That gas then goes through a turbine. That turbine then spins a shaft. That's mechanical. And that shaft then spins a whole bunch of magnets. And those magnets produce electricity. So we have gotten a whole bunch of different forms of energy going through this system. Now, with all those types, something that we care about in thermodynamics is how efficient is that system going. Because you can think about it like a pie. I'm going from 1 to 2 to 3 to 4, and I start off with a whole pie. After I transfer from nuclear to thermal, maybe I only have missing a slice. And I go from nuclear to mechanical, maybe I'm missing some more slices. And when I get to the end, how much of that energy actually made it to doing something useful, like powering my, pogo sticks, or letting me cook a meal. I don't actually have a pogo stick. If I could do that, that would be pretty awesome. Sadly, I'm not that cool. That's okay. That's okay. Now let's focus in on the other forms of energy, the macroscopic forms that we're more familiar with, you're going to deal with quite a bit. And they are kinetic and potential. So kinetic is all based on motion. As a note, that's relative to some reference frame. Like currently, I'm sitting fairly still in my office. So I could say that relative to where I am right now, I have no kinetic energy. I have no relative velocity compared to the ground. But I am on a planet that is rotating. I'm on a planet. Let's try to draw the planet fairly well. Okay, and some other countries. And that is rotating, it's spinning. And that guy is also going around a star. And this is part of a galaxy which is moving very, very fast. So I have all kinds of motion right now. Like technically I'm moving very, very fast relative to some completely stationary observer in the universe. But we don't deal with magical stationary observers in the universe. We deal with our own reference frame. So, for me, that would be right now to the ground. If I start moving, then I'm moving, I have a velocity compared to the ground. The other one is potential energy, which is all about how high you lift something. That's the Z right there. And I say potential energy, there's actually various types of potential energy. We're focusing on gravitational potential energy. Now, the way I like to describe potential energy is simply saying that it gives you the potential for movement, the potential to do something useful. Like, for example, if I take a ball, and that ball right here, okay, it's on the ground. If it's just sitting there on the ground, not moving, then it's not doing anything. It doesn't have the potential to do any work. It's not moving. It's not going to just suddenly start moving. However, if I then take that ball and I put it in the air, it has gained potential energy. It has a potential for movement. If I let go of it, it will fall. And if it falls, I can maybe do something useful with that energy. And interestingly enough, if I got rid of all the air resistance, all the friction, anything that might get rid of energy, and I were to measure my ball's kinetic energy just before it hit the ground, I would find that that potential energy actually equals that kinetic energy. Pretty cool stuff. So now let's look at this car right here and think about this situation. Now, as the car goes up the hill, its potential energy is going to increase. Why? Because it's going up. It's going up a distance z. Now, what about its kinetic energy? Its kinetic energy, on the other hand, is going to be based on what the car is doing itself. It isn't based on how far it's moved. It's not even based on, well, it's based on how fast it's moving, but the change is not based on how fast it's moving currently. The change is based on if it's changing. So if I'm accelerating, okay, then that means that my car's kinetic energy is increasing. If I'm decelerating, then it's decreasing. If I'm not accelerating, so my velocity is constant, my kinetic energy is constant. It's not changing. But so long as I'm moving, I have kinetic energy. Okay, I know I just blew up a whole bunch of equations here, but do not worry, they're all being repeated quite a few times. So one little error here, this is supposed to be a lowercase ke, not an uppercase ke. And while you're seeing all these equations, we've already seen this one, these two before, and these two before. The only difference is this, and you need to notice this, and you need to make sure you remember this. Capital letters are just energy, or entropy, as we'll learn about later, or exergy. Other things we'll learn about later. Lowercase letters are energy per unit mass. Okay? This equation right here is for my total energy, and it's simply adding my kinetic energy, my potential energy, and my internal energy, which is connected to temperature. Now, why per unit mass? Well, because often I might be thinking about, let's say I have a piece of coal right here, okay? And I set that on fire. I can use that energy to then produce electricity. Okay, so how much electricity can I produce? Well, I might find out it can produce 50 kilojoules of energy. And that was 1 kilogram of coal. Well, then that means that's 50 kilojoules per kilogram. I'm trying to figure out how much energy I can get out of a particular amount of fuel, because that tells me how efficient I am. If one system can get 100 kilojoules out of 1 kilogram of fuel, another one can only get 50, well, the 100 kilojoule is much better. So per unit mass gives us a way to normalize. So I'm not looking at a factory and saying, wow, it's producing a billion, quadrillion units of energy. Well, it might be doing that very inefficiently. So if we do it per unit mass, we can see how efficient it is at using its fuel. Okay, now down here you'll notice I have an E dot and an M dot. Well, those are all talking about how things change over time. So M dot is simply equal to dm dt. How is the mass changing with time? Okay, well, let's figure this out. So I've got these equations here. So the mass flow rate is equal to my density times the area of wherever it's passing through times the average velocity. Once again, that is velocity. And the area in many cases is circular, and so you'll often be given a diameter. If you are, this is how you calculate the area. But one other thing you can think about is this. Area times velocity is another quantity which we can call the mass flow rate. So that's density times volumetric flow rate. So that's the volume flow rate. That one right there is volume. So you got to be very careful about that, because you'll see a capital V. You're like, wait a second, why is a capital V there and capital V here? It's confusing. It is confusing. Personally, I always use lowercase v's for velocity and capital V's for volume. But your book uses capital V's for both, so I'm trying to keep the same notation. Now you'll see things flowing through pipes a lot, or escaping through pipes a lot in the next few chapters. So make sure you don't forget this, because we're going to come back to it quite a bit. Okay, that's it for next time. We're going to be jumping, or that's for this time. And next time we're going to jump into an example. So I'll see you all then. Bye-bye.